Welcome to our lecture on work, energy, and power. These concepts are fundamental in physics and appear in various contexts from daily life to advanced applications. In this video, we'll cover the following topics. First, we'll introduce the basic concepts of work, energy, and power. Then, we'll explain the scalar product method used to calculate work. Finally, we'll derive and explore the work-energy theorem, which relates work done on an object to its change in kinetic energy. Let's begin with the concept of work. In physics, work is done when a force causes an object to move some distance. Mathematically, for a constant force, work is defined as the product of the force in the direction of displacement times the displacement. Let's understand this with some examples. When you push a box across the floor, you're doing work. The force is your push, and the displacement is how far the box moves. But if you're holding a heavy box stationary, even though you apply a force, you're not doing any work in the physics sense because there's no displacement. The SI unit of work is the joule, represented by J. 1 joule equals 1 Newton meter, meaning the work done when a force of 1 Newton moves an object 1 meter in the direction of the force. Now, let's move on to energy. Energy is the ability to do work. It exists in many forms, but the two main types we'll discuss are kinetic energy and potential energy. Kinetic energy is the energy of motion, and potential energy is stored energy due to an object's position or condition. Next, let's discuss power. Power is the rate at which work is done or energy is transferred. Mathematically, power equals work divided by time. Now, let's explore how to calculate work using the scalar product method. The scalar product, also known as the dot product, is used when the force is not in the same direction as the displacement. The formula is work equals force dot product displacement, which equals the magnitude of force times the magnitude of displacement times the cosine of the angle between them. Let's consider some special cases. When force and displacement are parallel, theta equals 0 degrees, and cosine of 0 is 1. So, all of the force contributes to the work. When force and displacement are perpendicular, theta equals 90 degrees, and cosine of 90 is 0. So no work is done, regardless of the magnitude of force or displacement. Finally, when force and displacement are in opposite directions, theta equals 180 degrees, and cosine of 180 is -1. So the work done is negative. Let's now derive the work-energy theorem. This theorem states that the net work done on an object equals the change in its kinetic energy. Mathematically, W equals KE final minus KE initial. Let's derive this theorem using Newton's second law. We know that the net force equals mass times acceleration. The work done by this force over a displacement d is the integral of F dot ds. Substituting Newton's second law, we get work equals the integral of ma dot ds. Using the kinematic equation v dv equals a ds, we can rewrite this as m times the integral of v dv. Integrating, we get m times 1/2 v squared evaluated from the initial to final velocity, which simplifies to 1/2 mv final squared minus 1/2 mv initial squared. So we've proven that the work done equals the final kinetic energy minus the initial kinetic energy. This is the work-energy theorem. Let's apply the work-energy theorem to a practical example. Imagine a 2 kilograms ball initially at rest. A force of 10 newtons is applied to it over a distance of 5 meters. To find the ball's final speed, we'll use the work-energy theorem. First, the work done, W equals force times distance, which is 10 newtons times 5 meters, equals 50 joules. The initial kinetic energy is 0 since the ball is at rest. From the work-energy theorem, we know that the final kinetic energy equals the work done plus the initial kinetic energy, which is 50 joules. Using the kinetic energy formula, 1/2 mv squared equals 50. So v equals the square root of 100 divided by 2, which equals 7.07 meters per second. Let's summarize what we've learned. Work is the energy transferred when a force moves an object through a distance. Energy is the capacity to do work, with kinetic energy being associated with motion and potential energy with position. Power is the rate at which work is done. The work-energy theorem states that the net work done on an object equals the change in its kinetic energy, providing a powerful tool for solving mechanics problems. Thank you for watching this video on work, energy, and power. These concepts form the foundation for understanding many phenomena in physics, from simple machines to complex systems. In our next video, we'll explore conservation of energy and its applications.